Hello, welcome to another lecture, and today we'll be discussing about the Diffie-Hellman key agreement protocol. Before moving to the protocol, let me just tell you briefly that on the key distribution and management, there will be various videos that I'll be creating, and chiefly they will be divided into three categories. The first category is today what we're discussing. This is symmetric key agreement. So you have to keep in mind that when we are talking about key management, so there are keys of two kinds. One is your secret key. Secret key is used when we are talking about the symmetric key algorithms. So they are both the parties who want to communicate or send messages to each other will be having the same secret key that would be used for encryptions and decryptions. Then there is public key crypto system in which you have got two keys, a private key and a public key. And the private key has to be kept private because you have got a generator, you generate the value, keep the private key with yourself. Public key has to be distributed, and therefore in public key distribution certain other kinds of methods are used, and in that we'll be discussing about the public key infrastructure and the certificates that are used for the sharing of public key and other topics. So these are the two broad categories. Now in symmetric key distribution we will be using a trusted third party, and the protocols that use that third party for the distribution of the key will be covered in a separate video. Today, what we are talking about is the symmetric key agreement. Here, no third party or no key distribution center is required. The two parties who wants to send message to each other will be sharing certain information publicly, and that information will lead to the creation of the keys. And those keys would be used for the encryption and decryption for further communication. So let's look into the Diffie-Hellman key agreement. It is a mathematical approach. There are two parties, Alice and Bob, and they want to send messages to each other. So what Alice does is that they will select two values, n and g, and which are the public values. N is a value that would be required for the calculation of the mods, and n is supposed to be a large prime number, and g is any value which is in the domain of n minus 1, and that is also part of the group which has got its group properties over the multiplication operation, and Zn is star domain, and n is supposed to be a prime number, large prime number. Remember from RSA we said that that prime number should be of the order 300 decimal digits, right? So you have to take a very large value of n. Once you have these two values, then Alice and Bob will have a secret value with themselves. Alice is supposed to know a secret number, that is x, which should not be told to anybody else. And similarly, Bob will assume a value y with itself, and that y should not be told to anybody else. These are absolute secret and they should not be revealed at any cost. So the first step is that Alice uses that secret information x that Alice has and calculates the value g to the power x mod n, and this value is called as r1. This r1 will be sent to the Bob over the channel. Now this r1 is a message that could be intercepted by any intruder. So it's an open channel, anybody can read it, right? So g to the power x value has reached to the Bob. Now Bob will be calculating r2 value with g to the power y mod n. Now g and n are known to everybody. Y is a secret with Bob. So once these two messages have been exchanged, now what Alice does is Alice calculates r2 to the power x. Why? Because r2 is the value that is received from the Bob, and x is something that Alice knows, and therefore Alice was using x for the calculation of the exponentiation. And similarly, when Bob has received r1, it will be calculating r1 to the power y mod n. Now if I evaluate these two values, then you will find that r2 is g to the power y mod n. So if I replace r2 by g to the power y to the power x, so the key comes out to be g to the power xy. And similarly, the key calculated by Bob with r1 to the power y, r1 is g to the power x, so g to the power x to the power y is equals to g to the power xy. So both will agree upon the same value, that is k. Now this is a very simple mathematical approach. Anybody can use it for sharing of information, but you will realize that if you are taking small values of x and y and j and n, then it is very easy to break it down. First of all, the possible attacks that it has is the discrete logarithmic attack. So if you have got anything in the exponential powers, you perform a logarithmic attack onto it. And we said that discrete logarithmic attack is a polynomial time problem if you are taking small values. But this becomes a very difficult task when the values are really great. You will also see that in the calculation of the key at Alice is having two-third information and one-third information is from Bob. For the calculation of key at the Bob's end, it has got two-third information by himself and it gets one-third information from Alice. Right? So both are collaborating in creating the keys. The problem here is if you are taking small values, anybody can intercept R1 and R2, get the values of g to the power x and g to the power y. They know g, they know n because they are public, these are public values. If you've got small numbers, they will simply perform a discrete logarithmic attack and they will easily calculate the value of g to the power x, y. So the solution is that you take a very large value of n, as I said in the beginning. It has to be a prime number and it has to be in the order of 300 decimal digits. Then you have to take a value of g that is in the domain of n minus 1 and should have at least one very large factor that is about 60 digits of a number, and that too belongs to the Zn star domain over the multiplication sign. And these two parties also need to have large values of x and y with them, and these values of x and y should be immediately destroyed as soon as the key has been created. Right? If you are following these steps, if you are taking such large values, then performing discrete logarithmic attack is a difficult task and you won't be able to achieve it in polynomial time. That is one of the attacks. The second kind of attack is man in the middle attack. Now, if you have seen from this example, there was no way Alice and Bob were throwing challenges to each other in order to identify that the entity who is sending the values of R1 and R2 are the entities as they claim to be. Right? So, in no way Alice can ensure that the message R2 is from Bob. In no way Bob can ensure that the message R1 is from Alice. That is one of the that is the other problem with this agreement. And here the intruder can now jump in between and it can intercept the first value from the Alice, that is R1, which is g to the power x mod n. What it does is now it calculates the value g to the power z mod n, because intruder is not supposed to know the value y because y is secret to Bob. Therefore, intruder will send a value R2, that is g to the power z mod n. It will send the same value to the Bob as well. To Bob, it will appear that somebody is trying to contact me and thereby he or she is trying to create a key with the Bob. So R2, when received by Bob, Bob will be calculating the value of g to the power y mod n and will be sending to the intruder. Intruder again intercepts this message and does not send this message to the Alice. Now what happens towards the end is, based on the information intruder has exchanged with the Alice, Alice would be creating a key by R2 to the power x mod n calculation. Bob would be creating a key by calculating R2 to the power y mod n, because Alice has got x as his secret and it has got y as his secret, and intruder would be calculating two values, k1 and k2 both. So based on the value it receives from the R1, it calculates R1 to the power z, and based on the value it receives from Bob, that is R3, it calculates R3 to the power z mod n. By the calculation of R1 to the power z, it is getting the value of g to the power xz, and here the same value would be calculated by the Alice. So the key established between Alice and intruder is g to the power xz mod n, that is k1, and k2 is the key that is established between the intruder and the Bob, which is g to the power yz mod n. Now, since both the parties, Alice and Bob, were not authenticating each other and were simply creating the keys based on the values that they received using the Diffie-Hellman key agreement, therefore they were able to establish the keys, but they were not able to verify that the message that they are expecting is from Alice himself or somebody else. So here intruder has created two separate keys. Now, based on these key values, whenever Alice sends a message thinking that the Alice is sending a message to Bob, will be intercepted by the intruder. And since that message is supposed to be encrypted by K1, can easily be broken down by the intruder, because intruder also has got this information K1. Intruder can modify or create a new message by himself and use key K2 for encryption. K2 is the key that is created by Bob also, and the Bob would be easily able to decrypt it. And in this way, intruder can easily modify the messages intruder can easily control the flow of the messages. Intruder can easily control what kind of a message and what content of the message could be sent to the Bob and the Alice, right? Now, man in the middle attack, why did it occur? The reason I have been telling again and again is that you were not able to identify or authenticate the entity being involved in the communication. And if you refer to my previous lecture that was on entity authentication, there are several schemes that we have discussed, and we have also seen that digital signatures could be used for entity authentication. So, based on that, I would like you to think about a solution to prevent man in the middle attack in terms of digital signatures. What modification should be made to such a scheme so that man in the middle attack is prevented? Thank you.